Welcome to the deep dive. Today, we're tackling something vital, a resource that's literally all around us, but, still out of reach for billions. Water.
That's right.
We're going deep into atmospheric water generation, AWG, basically pulling clean drinking water right out of the air. You might have seen ads, maybe for something called the air fountain system.
It does sound a bit sci-fi, doesn't it? But the science behind it, well, it's incredibly important.
So our mission today.
Yeah, our mission is pretty clear. We need to cut through the marketing noise. We're going to look at the crisis that's driving this tech forward.
Okay.
Understand the two main ways it works. One's kind of old school, the other is pretty revolutionary. And figure out, the real world usefulness, the cost, the upkeep, everything you, the listener, need to know to see if it's actually practical.
And we really have to start with just how bad the water crisis is. Because that's really the whole reason we're even talking about this. The numbers are just, well, they're staggering.
They really are. The UN reports, they paint a stark picture. Around 2.2 billion people don't have safely managed drinking water right now.
2.2 billion.
Yeah. But to really grasp the urgency, you need to look at SAML scarcity. About half the world's population deals with severe water scarcity for at least some part of the year.
Half the world.
That's like 3, maybe 4 billion people facing real stress. It impacts their health, food security, their whole economic situation.
And that's way more than just, not having water from the tap for a bit. When half the planet has this issue, it's not just personal inconvenience. It can lead to mass migration, instability between countries, huge economic losses.
Exactly.
We often forget, I think, that for so many, getting water isn't easy. It's a daily job, often for women and kids, taking time away from school or earning money.
Precisely. And that urgency, that's what makes AWG so attractive.
Yeah.
Your traditional sources, rivers, groundwater, big pipelines, they're either drying up, getting polluted, or just aren't where people are. But the atmosphere, it always has moisture. So grabbing that vapor gives you a local, distributed, and potentially really resilient water source.
Okay, let's talk scale then. When we hear about something like the air fountain system, is this like a little desktop gadget, or can it actually support a household?
Well, air fountain system is often just a product name, kind of a catch-all for those home-level portable AWGs.
Oh, okay.
These units are usually designed to pull humidity from the air around you, condense it, filter it, for household use. They typically make maybe 5 to 30 liters a day, in that range.
But the tech itself goes much bigger than that, doesn't it? You mentioned centralized systems are struggling, but we do see these larger AWG units being used.
Oh, absolutely. The scale varies wildly. On the big commercial end, you've got companies like WaterGen, for instance. They build systems for hospitals, military field deployments, community centers, units producing thousands of liters daily. So yeah, while the small home unit gets a lot of buzz, this tech really spans from personal use right up to potentially supplementing municipal supplies.
Right. Okay. This is where it gets really interesting for me, the how. There are two basic ways to do this, and the difference seems huge, especially for your electricity bill. Let's start with number one, cooling and condensation.
This is the one most people are familiar with, even if they don't realize it. Think about your air conditioner or a dehumidifier.
Okay.
It works by cooling air below its dew point. Simple idea, really. A fan pulls air across a really cold surface, usually an evaporator coil.
Like the cold part inside your fridge.
Sort of, yeah. When the water vapor in the air hits that cold coil, it cools down fast, turns back into liquid water condensation, and drips into a collector.
And then that collected water gets filtered, maybe hit with UV light for purification, and boom, drinking water. Sounds simple enough,
right,
but this is the method that's really tied to the weather.
Critically tied, yeah. Its efficiency, how much water you get for the energy you put in, is completely dependent on the air temperature and, crucially, the relative humidity.
So hot and sticky weather is good.
Exactly. Hot, humid places like coastal areas, these machines work reasonably well, but take it to a drier place, maybe the U.S. Southwest or many desert regions, or even just a cool, dry day anywhere.
Yeah, what happens?
Then the output plummets. You might be burning, say, 500 to 1,000 watt-hours of electricity just to squeeze out 1 liter of water.
Whoa, wait, let's break that down. 1,000 watt-hours is 1 kilowatt-hour. If electricity costs, say, 15 cents per kilowatt-hour, that's 15 cents per liter. That starts sounding way more expensive than tap water, unless you have super cheap or free power.
Precisely. That energy cost can be prohibitive.
That efficiency issue seems like a massive hurdle for large parts of the world. If the standard method doesn't work well in Arizona, we need something else. Which I guess brings us to Approach number 2.
Exactly. Approach 2, sorbent or desiccant-based harvesting. This is where the real cutting-edge stuff is happening. It's what could make AWG truly viable in those dry or cooler climates.
Okay, sorbent, like silica gel packets.
Kind of like that, but much, much more advanced. Instead of just brute force cooling the air, these systems use special materials that actively uh, grab onto water molecules even when there aren't many around.
So it's not about cooling, it's more like chemically attracting the water.
That's a good way to put it. It's less about condensation, which is a physical change, and more about absorption water molecules sticking to the surface of this material. Think of it like molecular Velcro, but just for water.
Molecular Velcro, I like that. What are these materials?
There are a few types. Engineered salts that are highly hygroscopic, meaning they readily absorb moisture. Specialized polymers, too. But the real excitement is around things called metal organic frameworks, or MOFs.
MOF.
Yeah, MOFs. They're these incredible, porous, crystal-like materials. Imagine a sponge, but with a massive internal surface area at the molecular level. They can selectively trap water molecules even when the relative humidity is down as low as, say, 15%.
15%, that's seriously dry air. That's a game changer compared to the cooling method.
Absolutely. It opens up possibilities for arid regions that were basically off limits for traditional AWG.
Okay, so the MOF grabs the water. How do you get the water back out?
You add heat. Gently heating the sorbent material makes it release the water it captured, but now it's concentrated water vapor.
Ah, so you concentrate it first, then condense it.
Exactly. And condensing that concentrated vapor is much easier and takes less energy. Plus, and this is key, the heat source doesn't have to be electricity.
What else could it be?
You can use low-grade heat. Think solar thermal collectors basically using sunlight to create heat directly, or even waste heat from factories or generators. This dramatically lowers the running costs and makes these systems potentially truly off-grid.
That sounds much more sustainable.
Yeah.
Okay, let's shift gears a bit. Let's talk pros and cons. For someone listening, thinking about this tech, what are the biggest advantages, the real selling points?
Well, number one has to be that distributed, resilient source aspect we talked about.
Right, water where you need it.
Exactly. Remote homes, disaster areas, places without reliable pipes. It reduces dependence on that big, fragile infrastructure that can get knocked out by storms or, other issues.
And the water quality argument seems strong too. Since you're basically collecting distilled water vapor initially, you avoid a lot of the ground contaminants, right? Like heavy metals, pesticides, nitrates, stuff you might find in well water.
That's a significant potential advantage, yes. The starting point is pure H2O vapor. But
There's a but. I sensed a but. What about air pollution? If I'm running this in a city with smog or near industry, aren't I sucking that pollution in with the water vapor?
that is a really critical point. Yes, you absolutely are concentrating whatever is in the air. So while you might avoid groundwater contaminants, you must have excellent filtration to deal with airborne stuff.
Like what?
Particulates, soot, bacteria, viruses, volatile organic compounds, VOCs, and I think floating around. That means good quality AWGs need multi-stage filtration, typically activated carbon filters, maybe reverse osmosis in some, and definitely UV sterilization as a final step.
So the purity claim only holds up if the filtration is good and maintained.
Absolutely. Which leads us nicely into the cons, the reality checks.
Okay, let's hear them. What are the big watch-outs?
Well, we've hit on the main one already. Energy consumption, especially for those traditional cooling units.
Right, the high electricity cost per liter in many climates.
Exactly. Unless you're pairing it with cheap renewables, it can be very expensive water. This is why looking at those sorbent systems, especially solar thermal powered ones, is so important for long-term economics.
Makes sense. And you just mentioned maintenance related to filtration. That sounds like another big one. This isn't a plug-and-play appliance forever, is it?
Definitely not. Far from it. You have to think about the life cycle costs. Filters need regular replacement. UV lamps burn out. The collection tank needs cleaning to prevent biofilm or bacteria growth.
Biofilm. Yuck.
Yeah, if you don't maintain it properly, the storage tank can become a source of contamination itself. So for someone buying a unit or an aid group deploying them, you have to factor in the ongoing cost and hassle of replacing filters and keeping it clean.
That's a really important point, especially for aid work. If the community can't get or afford the replacement filters down the line, that expensive machine just becomes useless junk.
Sadly, that does happen. And the final big con, I'd say, is still scale. As cool as this tech is, it's currently tough for AWG to compete with the sheer volume and cost effectiveness of large, centralized water treatment plants for supplying, a whole major city.
So it's not replacing city water systems anytime soon.
Not for massive populations, no. It's more suited for specific niche applications right now. Households, small communities, specific facilities. It's a tool for resilience and decentralization, not quite a replacement for big infrastructure yet.
Okay, so connecting all that, where does AWG make the most practical sense today? Where can it have the biggest impact right now?
Well, the obvious ones are off-grid homes, remote cabins, maybe RVs or boats. Military field use is another big one.
Sure.
But the real sweet spot, I think, is in humanitarian aid and disaster response. Getting clean water quickly into a place where infrastructure is destroyed or never existed. And also maybe supplemental supply in cities that face those day zero drought scares, where the main system is failing or the water quality suspect. It provides a safety net.
That makes sense. Reliable drinking water when the main tap fails.
Yeah.
Okay, that's the picture now. What about the future, say 5 or 10 years down the road? What breakthroughs could really change the game for AWG?
Material science is moving fast. Those MOFs and other sorbents, they're constantly getting better. We'll likely see materials that grab even more water from drier air and, crucially, release it with less energy, less heat required.
Lower energy needed means lower cost.
Exactly. That drives down the cost per liter and makes AWG viable in more and more places, especially the really arid ones.
And you mentioned linking with renewables before. That's got to be a big part of the future too, right?
Oh, absolutely. We're moving beyond just slapping a solar panel onto a standard AWG. We'll see more deeply integrated systems. Imagine a unit where the solar thermal collector is designed specifically to provide the low-grade heat needed to regenerate the sorbent material. No complex electricity conversion needed for that step.
That sounds much more efficient.
It is. That kind of synergy is what will really unlock affordable off-grid water production.
Okay, and what about that idea you touched on earlier, buildings themselves becoming water collectors?
Yeah, that's the really exciting further out vision, architectural integration. Why just put solar panels on a roof? What if building facades, roofs, even walls could incorporate materials or designs that passively or actively capture atmospheric moisture?
So the building itself becomes a water source.
Potentially, yes. Architects and material scientists are exploring this, turning our built environment into active water harvesters. It's a fundamental shift in thinking about urban infrastructure and resource management.
Wow. Okay, that's a fascinating long-term vision. But let's bring it back to today. For you listening, if you're seriously thinking about getting an AWG for your home or maybe for a community project, let's run through a quick practical checklist.
Good idea. Number 1, check your local climate. Seriously, look up your average relative humidity. If it's consistently below, say, 30 or 40%, a standard cooling-based AWG will likely disappoint you with its output.
So if you're in a dry place, you really need to look into those newer sorbent-based systems.
You absolutely do, or at least have realistic expectations about a condensation unit's performance.
Okay. Point 2.
Calculate the lifetime costs. Don't just look at the purchase price. Factor in your electricity costs per kilowatt hour, estimate the energy use per liter for your climate, and find out the price and replacement frequency for filters and any UV lamps. Get the whole picture.
Right. Number 3.
Demand independent proof of water quality. Don't just trust the marketing slogans about purest water. Ask for independent lab test results showing the water meets recognized drinking water standards, like NSF or WHO guidelines. Especially important if you're in an area with air quality concerns.
Good point.
4th, plan for maintenance. Understand what's involved. How often do filters need changing? How do you clean the tank? Be honest with yourself. Are you prepared to do that regularly? Because if not,
It could become a health risk instead of a solution.
okay.
And finally, number 5.
Explore hybrid options, especially regarding energy. Can you power it with solar panels? If it's a sorbent system, is there a way to use solar heat or maybe waste heat from another source? Anything you can do to lower that operational energy cost per liter makes it much more viable long term.
Excellent checklist. So wrapping up, atmospheric water generation. It's clearly not some magic fix for all the world's water problems.
Yeah, definitely not a silver bullet.
But it is a genuinely powerful tool, isn't it? A decentralized, resilient option that adds to our water management strategies. It complements conservation, it complements protecting existing sources, it complements good infrastructure.
Exactly. It expands the toolkit, especially for homes, for disaster zones, for remote communities. It gives an on-site, reliable source where maybe there wasn't one before.
And perhaps the final thought to leave you with.
Yeah, the road ahead seems to involve this shift in perspective. Just like we now see roofs as places to capture solar energy, maybe we need to start seeing the air itself and even our buildings as accessible sources of water. We're just beginning to figure out how to turn on that tap efficiently. The air isn't just for breathing anymore, it's a vast, untapped reservoir waiting for us.